Okay, so good evening, everyone, and a very warm welcome to another episode of NDT Talks by OnestopNDT. We are excited to have you join us for our May session, where we explore a topic that is redefining the future of inspection. So we were talking about the important questions about this transformation. The questions are robotic systems truly ready to replace human inspectors in critical scenarios? How reliable are autonomous inspection decisions? And what role does NDT play in enabling these systems to deliver accurate, actionable insights? To explore these questions, we have a panel of experts working at the intersection of robotics, automation, and inspection technologies. So, joining us today are Dr. Camelo, Research Fellow specializing in robotics and NDT integration, Devpal Ghoshar, robotics engineer focused on inspection, automation, and industrial robotic systems for hazardous environments. Dr. Abhishek, technical lead at NDT Suit, working on advanced inspection solutions and digital systems. We have Vincent Massol, business development and application specialist at Nimbold, building robotic solutions for industrial inspection challenges. Moderating today's discussion is Marcus, a solutions consultant and specialist in training who will guide us through this conversation. With that, I'll hand it over to Marcus.
Thank you. I hope you can all hear me well. We've fixed all the connection issues, hopefully. Thank you for the introduction and welcome everyone. Welcome Dr. Carmelo, Devpal Ghoshar, Dr. Abhishek and Vincent Massol. Yeah, great to have you on board. So robotics and autonomous systems are often presented as the future of inspection, especially in environments that are hazardous, repetitive, or difficult for human access. But in NDT, inspection is not just about data collection. It's about interpretation, judgment, and trust in the results. So today, what we're really exploring is this. Where do robotics and autonomy genuinely add value in NDT? And where do they still fall short? Is the industry moving forward towards fully autonomous inspection systems, or are we building tools that augment human expertise rather than replace it? So let's begin by grounding this in reality. So we're going to have a look at some questions together. So the first question to discuss is, where are we today? So from your experience, where does the industry currently stand in terms of robotic and autonomous NDT adoption? Are we seeing scaled real deployment, or are most solutions still in pilot, demo, or niche use cases? So if I can open that up to our panel of experts, perhaps you want to come in and have a look at this first question with me.
Yeah, I guess
Who's going first?
I can go first. So I have been working on automating NDT for aerospace, nuclear, and power generation industries at the factory level. So it's not in field or in service after deployment stage. This is while the components are being built. And as far as autonomous and robotic systems are concerned, they are used quite extensively at the factory level because very early on, we had to follow factory automation. When parts are being produced at a very rapid rate, NDT cannot be the bottleneck. So effort has been put in to a great extent. It's still slow. I think you pointed correctly that when it comes to the data interpretation, analysis, and reporting, there is still a huge human component involved. And that is not necessarily because of lack of technology. It is more because we are a very conservative industry, and techniques have to be approved before they go out there.
Mm-hmm. So just to kind of follow on that, do you think, or do you see that a large proportion of inspections aren't really automated? They are only partly automated, perhaps, when it comes to this kind of robotic
Um,
inspection?
I would agree, although automation is defined at different levels. There is the automation of physically moving the sensor. There is the automation of relating what component is being inspected, what are the inspection methodologies being applied, and parameters being applied. All those are being automated already. Like when you get a data file, you know exactly who did it, when was it done, what were the different parameters. When it comes to analysis, I think that's where the field is still quite wide open. There are
Yeah.
certain scenarios where automated analysis is feasible and possible. In others, it's more semi-automated, and then there are very critical industries where a human has to take a look at the data.
Yeah. Yeah. So there's still interpretation happening right at the kind of no go or go point for that part or critical component. Okay. Um, so this is in this particular application you're talking about is more kind of space based. You're talking about in the factory.
Space power generation, it's in the factory. It's
Yeah.
where the parts are being manufactured. Yeah.
Yeah. Okay. Uh, 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 just coming back to the other members of the of the board, what are the experiences from the others here? Maybe from Dr. Carmelo or Devpal and Vincent. Perhaps you have some input as well.
Yeah, thank you, Marcus. Thanks to OnestopNDT for organizing and inviting me. My work has been at the intersection of robotics, industrial sensing, and non-destructive testing for about 15 years. I am a researcher at the National Research Council of Italy, but I have also worked in other universities abroad, outside Italy. So my career is the career of a researcher. Okay, so I have worked on robotic deployment of several inspection and measurement methods, including ultrasonic and phased array inspections at the current sensing, thermography, and metrology-guided robotic systems. Many of these applications involved large or complex components where manual inspection becomes slow, variable, or difficult to reproduce. So my perspective is, okay, research driven, but it is quite pragmatic because the research has been funded by companies, especially aerospace companies. So what I can say is that robotics can be transformative in non-destructive testing, but only when the robot, the sensor, the data acquisition, instrumentation, and the inspection procedure are engineered as an integrated system, okay? So I will say that at the moment, adoption is real, but is uneven. So we are beyond the pure demonstration phase in several fields. But for example, in structured manufacturing environments, high-value components, large area repetitive inspection, environments where the inspection can be dangerous, and in some in-process monitoring applications, we are beyond the demonstration phase. But if we look across the whole NDT industry, I will not say that fully autonomous inspection is yet the norm, okay? So much of the market is still manual, semi-automated, or robot-assisted, rather than truly autonomous. So the scaled deployments tend to happen where the geometry is well known. The inspection task is a task that must be repeated over and over again. The business case is strong, and the inspection procedure can be qualified. So from my own experience, the technology works best when we stop thinking of the robot as simply a mechanical arm, and we start thinking of it as part of the inspection instrument. Okay, so maybe I stop here to leave space to the other panelists as well.
Yeah, thank you, Dr. Kamala. This is very insightful. Thank you for your input. So just from the remaining two panel members, Devpal and Vincent, perhaps you have some feedback as well or experience to share with us.
Yeah. I quite agree with what was said already. So thank you first for having me on the board today. That quite interesting question. First, my trivial opinion. I would say the adoption is poor right now for robotic in the industry in general, for the NDT in particular. Myself, I don't. I feel like we are facing a big issue, which is the consumer market, because robotic is same as AI right now, is something that everybody is talking about everywhere, and we have all those humanoid robots popping up everywhere on the internet, and the asset owner at the end of the day, those making the decision for purchasing a system, they are influenced by that also, and they are confused about what a robot is and what it's supposed to do and how it's supposed to do it. And accordingly to what was said just before me, we are not in the robotic business. We are in the application business. Robotic is just the technology, and we don't care very much about the technology. What we care about is having the job done, and this is really what we need to focus on. And in my background, I was working with big companies, Safran, GE, for example, and with suppliers like Olympus, for example. And I was able to witness that different kind of language, both words, one side the suppliers, the other side the asset owner, and they don't understand each other because they don't talk the same language. Although they use the same words, they don't talk the same language. Like when I was with Olympus, for example, Omniscan 2, Omniscan 3, we were so much excited about the new colors, the new rounded corners with the soft foam, etc. That was crazy, and we were saying this is the most up-to-date equipment. We were having the head on the heart, saying no software bugs, and the magical word, we were saying it's mature. And mature for people in the supplier side doesn't mean the same thing as the asset owner. For the asset owner, after that, I was with Safran GE, for example, and I can assure you, when we were purchasing an Omniscan or something else, nobody was excited in the office. The case was arriving on the desk and sitting on the desk for weeks before somebody opened it, because it's immature. Because maturity in an asset owner is 8 months later, after qualification, repeatability and reproducibility, gauges, etc., etc. So this is application versus technology, and the market, unfortunately, is driven by asset owner, is driven by application. And robot is just a mean, is not a goal. So that's I would, in my opinion and my experience on the my daily work on the market, this is the first big blocker or challenge we have. And the second one, big blocker, is the so-called ROI. Because many people, they think, many customers, let's say, markets, they think they will shift a human with something made of robotic technology. And they don't allow them, or they don't allow us, to rethink the process. And nobody said, or at least I never said myself, that the human design, the human body, is the best design. So why should a robot mimic a floated design as the human body? Like a valve. A valve is something round shaped, because in your mind, you know that if you turn it around, it opens something turning on the back. But this is just for design for human. And if you want to create a robot to turn that valve, fact is, you will create a crazy multiple axis thing with crazy fingers, whatever technology, AI, etc., to do a simple task a baby with no knowledge but strong enough could do. Whereas if you can remove the valve, put something else in place, to shift the valve with something else that has been designed for robotic maneuver or use, then you can think about a robot that will be efficient for that task, but more because of the ROI, that will be able to perform multiple tasks at one time. Because all those single human application we're trying to shift with robots, we need to design a dedicated robot, and then we cannot have ROI at the end of the day. So that's the second big issue I see on the market. That somehow it's forbidden to rethink the process, and then this is a blocker. And the best robotic projects on the market I've seen yet are the project where we start from scratch on a new manufacturing process. So then the design of the part and the design of the supply chain is driven by the robotic integration and not by the human body shape.
Okay, these are all good points, actually. Thank you for this. That's a good kind of introduction question. So it helps us to understand where we are today. Let's have a little think about the second question then. The engineering reality versus market promise. So there's often a gap between what is promised and what is delivered. We've kind of thought about that a little bit in the first question. And what are the biggest technical limitations you've seen when deploying robotic NDT systems in real environments? I think, Vincent, you spoke a little bit about that, about the physical limitations. So yeah, any more thoughts about this from our three members of the panel? So what are the biggest technical limitations you've seen when deploying robotic systems in real environments? So some of the things to think about here, just to kind of drill down into the question. What are the thoughts on navigation? So getting the robot to the right place versus inspection accuracy, which is harder? So which one of those two things is harder when looking at the inspection process? And then the data quality versus the positioning stability. So where do systems fail? Yeah, let's have a think about those kind of things. So maybe Dr. Carmelo, have you got any thoughts on this?
Yeah, very interesting questions. I will say that the biggest gap I see is between the robotic motion and inspection quality motion. What I mean is that a robot can move from point A to point B quite impressively, but non-destructive testing does not just require movement. It requires the probe or the sensor to interact with the part, to interact with the component in a controlled and meaningful way. And in real deployments, the problems are often at the interfaces. So what are the interfaces? The interfaces, for example, the interface between the robot and the sensor, between the sensor and the part surface, between the nominal digital model of the part and the real component, and between the acquired data and the inspection decision. So all these ones are interesting interfaces that do not always work perfectly. Small errors, for example, in tool calibration, part registration, probe angle, standoff, coupling, cable behavior, or surface condition, part surface condition, can have, in my opinion, and in reality, actually, they have a large impact on the quality of the non-destructive testing signal. So to me, the hardest challenge is not simply robotic manipulation or navigation or inspection accuracy in isolation, but the hard problem is maintaining the inspection validity throughout the path while the robot navigates. So navigation is necessary, but inspection quality navigation is harder, to answer the first question you made. So then where do systems fail? They usually fail where assumptions meet reality. So the digital model is slightly different from the real part. the surface of the part is rougher, maybe is rougher than expected. Coupling is not stable. The robot is repeatable, but not absolutely accurate enough often. And on the visualization of the data is crucial, because maybe we acquire a lot of data. The robot is very good at acquiring data, but then we need to be equally fast and accurate in visualizing and processing the data to meet the final interface from data to final decision.
Very good. Thank you, Dr. Kamalo. Any other thoughts from the other two members of the panel? So Dr. Abhishek or Vincent?
I think one of the most crucial places where robotic or autonomous integrations run into difficulties is the easy access to enabling technologies. I think Carmelo sort of hinted on it as well, that the ability to move a robot to a position is different from the ability to correctly encode the data that was collected at that position. And these are enabling technologies that need to be developed in order to do this effectively. And over the last, I would say, 15 years, that's sort of how long I have been involved. I think others probably have a much deeper experience on it. But over the last 15 years, what I have noticed is that these enabling technologies were developed on first off initial projects where people went into it not knowing what they were going to run in, what they were going to see. So basically, reality starts meeting expectations, and that's where I wouldn't necessarily call it a failure. What ended up happening is that these companies started developing and solving the problem. And it has slowly started to move beyond the original sort of applications or original systems where these technologies were developed from, and they are going and being applied across the board. The adoption is happening. I think at this point of time, when we run into implementing an NDT system, the first questions that we ask are no longer the kind of questions that we were asking 15 years ago. So there are a lot of things that we take for granted. Robots have been around for a while. There are certain things where you can simply go to an expert and find a solution. And for others, you have to go to these individual sort of entities who have developed these enabling technologies for what we are trying to do. I think Vincent touched upon that as well. Like you don't need a circular valve essentially to get information flowing. And one of the big places where we felt the biggest sort of aha moment was that these enabling technologies come from different areas of expertise. So the robotics enabling technology comes from that area that is not going to come from the instrument manufacturer. The advances in the instrumentation, a beautiful instrument with rounded edges and a nice interface, those are absolutely beneficial because you do want the instrument to be able to deliver what the user is eventually expecting with the data. And then it's on the integration end where all this sort of comes together into an efficient and optimized solution.
Yes, thank you. That kind of follows into our next question actually really well. Yeah.
If I may,
yes, yeah, go on, Vincent. Yeah,
I find it interesting also the experience from UTEX. I think we need also to look back a little bit in the past. Before we were talking about robotics, we were talking about special machine. That was the word before. Sometimes the word they change over time. And special machine was just gantry system, basically, immersion tanks for UTEX, for example. And like what I was saying before, the process were designed for the machine and not the other way around. If you look at jet engine manufacturing, and UTEX knows about that. Fan disc made of titanium. It was made mandatory to inspect those in manufacturing, so new products. And they designed immersion tank with gantry system and turntable. For that, they designed the complete supply chain around the immersion tank, and they didn't stop there. They created a special step in the forge process they called the pre-forge stage. So it's after it's raw, then it's pre-forge, and before it's machined. And that pre-stage is useless for the manufacturing process. It's mandatory for the ultrasonic immersion tank inspection. So it was created just for the ultrasonic inspection. And then to answer your question, then the engineering promises fits perfectly with the market expectation and what is delivered because it was adjusted. So when dealing about the top of the scale, jet engine manufacturing, super titanium alloy material, and crazy accurate parts, then it's quite easy to make a robotic application. And then when you move to outages, for example, refinery or things like that, you cannot have the same accuracy on the product. You have a blueprint of the refinery, and when you look at it, it looks all different. Nothing is the same place, same dimension, same diameter, etc. And then all of a sudden, your wonderful machinery, robotic stuff from the manufacturing plants, it misses the places, misses the thickness, misses everything. So then you need to adjust, and you need to have something for sensing, like the human body can sense and adjust smoothly, but the machine can just learn what we teach it, and it cannot discover something new. But here I think there's something that is just interesting also. In the same way we have robotic innovation, we have a second path, which is NDT innovation. And for one topic in particular, ultrasound, now you have stuff like plane wave imaging, total focusing methods, and interface correction. So you can also have systems where you have let's say a regular robot with regular accuracy that can first sense a surface, a part, a situation, then adjust the setup, and then make the inspection. And then it's not only the robotic, it's also the NDT technology that brings value to the market for in that example. I have I have an example in mind. GE, Waygate Baker Hughes, now Hexagon, since a week or two. They are top-notch CT manufacturer. I've used them. So when you buy it, 1.5 million, and you get a 30-ton marble system. That's crazy. And everything is so thick, so big, nothing moves. Its accuracy is crazy. But if the part has not the same accuracy, then everything fails. And in the other side of the scope, a couple of years ago, I met with NSI, for example. NSI, North Star Imaging something, I don't remember. They had a different system. They had a CT cabinet made of weak aluminum frames. So everything was shaking. and they changed the process where they made first an image of calibration balls, then they adjust all the settings, then they shoot the pictures of the part, then they do hand calibration on their balls, and then they correct everything. So here again, you can have some sensing steps first with your NDT technology in order to relax requirements on the robotic, maybe, and yeah, move those two leverages in the same time.
So different approaches. Okay. Thank you. Thanks, Vincent. Yeah, so we've looked at the engineering reality versus marketing promise. Yeah, let's look at the integration challenge a little bit more. We did talk about it here a little bit in this second question. Yeah, so robotics alone doesn't solve inspection, like we were just talking about here with Vincent. It needs to integrate with the NDT technologies. So what are the biggest challenges in integrating NDT methods into robotic systems? So things like UT, PAUT, ET. We were just talking about CT here. We talked about the coupling issues a little bit here. Vincent mentioned those, and Dr. Carmino as well. Surface conditions, calibration, and repeatability. What out of those things, what are the biggest challenges in integrating the NDT methods into your robotic systems?
Can I go first?
Yes, go for it.
Yeah, I agree with the viewpoints of the other panelists. So I highlight what has already been said. So the inspection method, the inspection method we want to deploy should drive the design of a robotic inspection system, not the other way around. So what I have enjoyed the most of my career in NDT research, in robotic NDT research, is that NDT methods are about physics. So we need to understand the physics of the NDT methods in order to develop good systems, good automated systems. So often what we see is that robotics makes NDT requirements more explicit, if you like. If we robotize ultrasonic testing, phased array ultrasonic inspection, eddy current, or thermography testing, each method brings its own physics and its own constraints. So for example, for ultrasonic or phased array inspection, probe orientation, acoustic coupling, incidence angle, surface curvature, water path for the coupling are critical, okay? For eddy current inspection, standoff and local surface conditions are also critical. For thermography, usually the challenge may be to get repeatable heating, the repeatable heating input, image alignment, part surface emissivity, and we need to, if we robotize thermography, we need to be able maybe to fuse multiple thermographic views into a final result for very big components. So my experience is that successful systems are not built by adding a sensor to the end of a robot. They are built by designing the robot path, the sensor deployment, the calibration routine, the data acquisition, instrumentation, and data visualization together from the start. So calibration and repeatability are really, really, really important because otherwise we cannot qualify, we cannot standardize the inspection systems. And for example, in areas like aerospace, that is, a very strict field, if things do not meet the standards, they cannot be like commercially cannot be adopted. So bringing calibration in the system, including ways and procedure to properly calibrate the measurement chain is crucial. Yeah.
Okay. Thank you, Dr. Camilo. Any other thoughts from the other panelists on this, the integration challenge?
Yeah, I can jump on what was just said. NDT is about the physics. NDT is actually a job. And NDT is actually a certification. And the biggest challenge for me is that the people making the technology, the robotic technology or the software technology, they are not into the physics, they are not certified. And worse than that, they never went in a plant or on an outage. And this is for me the biggest challenge, especially with new methodology like thermography, for example, phased array, because you achieve a picture and then all of a sudden they think, oh, I see the picture, I understand what I see, and I feel like I can make a call. But no, this is a job to make a call and to understand, etc. So this is the biggest challenge, how to create a team made of software people, robotic hardware people, and NDT people.
I want to look a little bit ahead after a system has been deployed. So a bunch of us come together, we build a system. We bring different areas of expertise to it. There's the ultrasonic physics, there's the automation, there is the integration, and it all is done to build a system. And this is where a lot of the systems start running into trouble, and that is cycle time. They suddenly realize that to do the essential tasks such as calibration, and then tuning the machine and getting it ready to scan starts consuming too much of the time that is available in a particular shift. So for certain parts, the calibration needs to happen pre and post inspection. For certain parts, the calibration needs to happen at timed intervals, every 4 hours, every 8 hours, once in a shift. And that's the norm. That's how NDT has been done. Those are expected tasks that need to be performed. So once a system has been commissioned, and 15 years ago, the commissioning, interestingly, was not on cycle time. It was one, can it do the things? And it was commissioned. It was good to go. And once the flood of parts started coming in, they started finding out that the system just does not perform at the level of production efficiency that's needed. And at that point of time, I think one of our integrators who works with robots, his words were, "We create industrial art." So it's beautiful, it's massive, it's very impressive. You walk people that were designed more from the technology end rather than from the end application end, ended up running into trouble. So for calibration, I'll give you a really interesting example. One of our customers who calibrates every 4 hours, they run the cal standard. I think it has like 35 or 50 inserts on it. You have to go and mark those inserts. You have to tabulate them, do the statistics on them, and then they say, is it good enough or not to proceed? And the first time we looked at the system and we finished it, we figured out that this process was extremely manual, and it would take half an hour to an hour of the 4-hour shifts just to calibrate the system. And that's really not acceptable when you're looking at efficiency. So we implemented a lot of very, very simple things. Have a map, bring the map back in, run the calculations automatically, take the calculations out, and instead of forcing the analyst to go into Excel and make a spreadsheet on it, just put those numbers in there. Computers are really, really good at that. It has nothing to do with robots or ultrasound or eddy current. It is simply a challenge of computing and mathematics, and you can put all that together, crunch the numbers for them, and I think we were successful in bringing the time down from half an hour to about 5 minutes. And even that is not good enough. Like the end customer is always coming up with new ideas on how can we do that even faster, because calibration is an essential process, but that is the downtime of the machine. It's not really making parts at that phase. So yeah, I think that's another thing to consider on this.
Thank you. So yeah, the integration challenge. It sounds like there's different elements to consider. So thank you for that feedback as well. Okay, let's have a look at our fourth question then. So this fourth question is basically looking at autonomy versus human oversight. So true autonomy means minimal human intervention. How close are we to fully autonomous inspection systems? And where is human expertise still absolutely critical? So we've talked a little bit about this already, about the actual point of the inspection process, where we have to basically make a decision. And who's making that decision? Are we using AI? Is it a human decision? Yeah, just to open that up again, let's have your input then from maybe Dr. Carmelo or Vincent, one of
Okay, I start first.
yeah.
That's okay with Vincent. Okay, in a nutshell, we are closer to autonomous inspection, autonomous acquisition, autonomous data acquisition, than we are to autonomous responsibility and autonomous accountability. The reason is what Vincent mentioned before. Like NDT is a job. Like, I mean, so far we have needed certified people to take decision, and that is still the case. So I think we need to separate autonomous data acquisition from autonomous inspection judgment. Autonomous data acquisition is becoming realistic in well-defined cases. Autonomous adaptation, so the capability of a robot to adapt the path to irregular surfaces or to geometries that differ from the theoretical CAD model. So autonomous adaptation is becoming realistic as well. So the system can map a surface, adjust the path, maintain a sensor response, and decide where to collect, maybe where to collect more data on the part. But fully autonomous acceptance or rejection of a critical component is a different thing. Is a different level of responsibility. So human expertise in this field remains essential in defining the inspection strategy, qualifying the procedure, understanding failure mechanisms, understanding the physics, as I said before, validating unusual indications, and taking accountability for the final judgment. So, in my opinion, artificial intelligence can be extremely useful as an assistant, but is not ready to be used to make the final decision. So AI can provide a huge help in screening large data sets, highlight indications, estimate uncertainty, guide adaptive scanning maybe, or prioritize areas of the parts that need further investigations. For critical NDT, I would not frame artificial intelligence as a replacement for the inspector. I would frame it as a decision support tool that must be qualified, must be bounded, and only if we manage to make artificial intelligence explainable enough for the inspection context. That's very important, because the inspection context is the context of keeping society safe. So we need something which is explainable, that can help us to get to the root cause of the defects. Okay. So yeah, I think this is my opinion on this question.
Thank you, Dr. Carmelo. Yeah, so it was my feeling also from what we discussed earlier, perhaps with the other panel members, that the human element is still very important from the sound of what you're saying now as well.
Can I add the final note, which I forgot actually? In NDT, usually are the rare cases that are often the most important cases. So that rare defect, that can lead to something unexpected, something that not even designers had forecasted. So in NDT, often we have rare cases. And a huge problem of artificial intelligence models is that often, well, you need to train those models. And how can you train a model on rare cases? That's a question. So, because I mean, by definition, rare cases are rare.
Yeah.
So
yes.
it's difficult to create a training data set on rare cases.
The
Okay.
factories
Yeah.
are designed to make good parts, not bad parts. So it's really hard to run into defects that happen because of process changes or other unknowns. So no, I totally agree with you on that. As far as AI's status today is concerned, it's an assisting tool. Now, one thing I do want to make an observation here, because I think we either on completely manual or we're completely AI. There's a middle path here which is automated, and automation does not mean artificial intelligence. Automation simply means doing a repetitive task over and over again with the same computational and mathematical rigor. When it comes to humans looking at data, and we're talking like 10 to 15 to 20 gigabytes of data, that's like, I don't know, how big is a movie? That's like 10 movies that you're playing, or the operator is looking at that amount of data, and he or she needs to identify a guy in a red hat who appears for a fraction of a second. So that's what we are asking our operators to do. And in this process, if we are able to automate how the human interacts with the data, that itself can provide quite a lot of improvement in efficiency, accuracy, and repeatability. Basically, take things that tire an operator out of the picture. So automation definitely is coming. I think I agree with Carmelo. There is currently completely relying on AI for critical components. We're not there yet.
Yes.
I totally agree with that, because the fact is, if you face a nuclear power plant failure, if you face a plane crash, or you spill oil in the water, what you want to do is put someone in jail. So you will never put AI in jail. So a responsibility is really talking about who is going to jail. So the one people with one name, with one NDT tag, we always have the responsibility to be accountable over a course in case of something bad happens, because at the end of the day, NDT is about preventing integrity issues. So this is the big responsibility over the shoulders of NDT people. AI is autonomy. AI is a machine that makes its own decision. And so this is totally prevented in the NDT. Algorithm, so software processing is very good, although on the other side, something that is quite shocking to me is now we have majority of digital NDT, so thermography, ET, CT, phased array, they all are digital. But for most of them, our assessment capacity is just the NDT guy high ability to dissociate two colors on a crappy screen. I'm talking about OmniScan again. Sorry about that. I promise I don't have any more talks about Olympus. But most of the people, they use the OmniScan with color palettes, and they make a call over the ability to differentiate a blue circle over a red circle. They say, oh, this is a defect. But the screen of the OmniScan is a Chinese supply, crappy screen, very far from a calibrated screen or something like that. But the data inside the OmniScan is so rich. The data inside is encoded 12 bytes on a dynamic DB dynamic that is crazy. And you can process a lot of frequency filters and frequency analyses inside those data, but the only thing they do is looking at time-based colors display on a crappy screen. So data processing, all of those digital data can bring so much value to the business, and we need computer assistants to process those big amount of data, because now they are digital, they are huge, and it would be too much time to do it manually. So that's for sure is a good support. And the total autonomy on a robot, I have an example of that. I'm working at the moment on some robotic topics with dogs for monitoring, surveillance monitoring in plants. So basically, the job basically is to walk the plant and check the pressure sensors. So pressure sensors, they are like clocks, like a watch, and we just need to get the camera close enough, capture a picture of that sensor, pressure sensor, and save it to a database. And then there is a read just to check whether it's in the green area or the red area. And this can be autonomous because the dog, he knows the path, and he goes from pressure sensor to pressure sensor, and he's completing his list. But so this is autonomous. And if you put something in middle of the path, he will make the decision of his own secondary path. So this is autonomy. But there is a man somewhere, can be another country, but somewhere there is a man checking that the list is complete, and also supporting the dog every time he's facing a blocker. So if he has something in the path and he cannot find a secondary way, he calls for human support. If he detects a sensor that is in the green or the red area, he calls for the support of a human. And at the end of the day, for the final report, if everything is fine, still it's a human that signed the paper. So it goes back to accountability and trial at the end of the day, and jail if it's needed.
Oh, okay. Thank you, Vincent. This kind of leads into our final question. We're coming towards the end of the discussion time, but we've got one more question just to look at here. So we're just going to look at the future. So we've talked a little bit about the possibility of AI now and whether that's working or not. But in the future, are we going to be looking at replacement or augmentation? So looking ahead 5 to 10 years, do you see robotics in NDT as a replacement for human inspectors? I think that maybe not from what we've talked about here, but as a replacement for human inspectors or a collaborative tool that enhances human capability. So what will define success in this space? So maybe if we go to Dr. Abhishek, perhaps, to kind of look at this with us first.
Sure. So I think the last hour we have spent talking is mostly about factory automation.
Yes.
And as far as the human inspectors in the field are concerned, they're not going away anywhere. I think they are critical to the assets. And I think Vincent may have mentioned earlier on, humans are pretty flexible, trainable sort of inspection machines. You cannot buy that kind of flexibility and that kind of intelligence on the market today. So as far as in-service and in-field automation is concerned, I think the effort is going to be more towards developing more and more tools that enable the operator or the analyst to make informed decisions. I think that's where the automation is going to trend on that end. In terms of factory automation, in terms of getting into hazardous areas, I don't think we really want to put humans in any dangerous positions as much as we can avoid it. So having autonomous robots that go into crawl spaces where generally you would try and put a human in those situations. You do not want to do that. I think that's where the robotics applications for data collection portion of it are going to grow quite a bit. When it comes to analysis, I think we have been looking at the use of machine learning and artificial intelligence through a more narrow lens. I think we've been looking at it from the point of making decisions for us. That's not where it might be the most or the best use of that technology. I think the best use of that technology is going to be to make the decision making more informed. For example, and I spent some time doing that stuff. We have deployed in certain for certain pieces of software the ability to just go run a model, find the back surface, and then basically create a back surface, front surface, and create a region of interest in ultrasonic data. That's it. That's the only thing that we use it for. Some of the base models we started out with are the ones that are used in biomedical engineering, just looking at blood vessels. You have a top part, you have a bottom part, and there's blood flowing between it. So there's a lot of cases where we can simply or more effectively use the models to clean up the data, to basically go to a point where you need an expert to look at it and say, oh, this is ring down versus this is a corner trap, to something where the data has already been cleaned up. Mostly running an algorithm or even a rules-based algorithm, and then presenting it to the user and say, what do you see there now? And obviously the big flaw would be there, because now the signal to noise, as far as the human brain is concerned, is a lot more reduced.
Hey, thank you, Dr. Abhishek. We have maybe time for one more panel member to give a bit of insight into this, and then we will move on to maybe our next section.
No, for sure, the future is collaborative. NDT technician will be there. NDT technician needs robotics in the sense we need an augmented NDT technician. So robotics can enable new capability for the technician, like Dr. Abhishek was saying. Hazardous environment, we have one which is confined space. Typically, asset owner, they want to prevent human from confined space entry. So we need the technician on site, but we need a technician with robots to penetrate the confined space. And we need that robot to be everything we said earlier, capable enough to perform the task in autonomy, or at least teleoperated.
Okay. Thank you, Vincent. I think from your answers there, we're looking at, in the future, in the next 5 to 10 years, more of a collaborative tool that enhances human capability rather than a replacement. I think that's the way we're looking at it at the moment. Okay, so let's just to kind of finish off the question section. We'll have a quick couple of rapid fire questions. So these are just short responses to the questions. So I'll open these up to you guys now. So first of all, one inspection scenario where robotics already outperforms humans. So just quick responses on these ones.
Disk inspection in jet engine manufacturing.
Yeah. Okay, thank you.
Large area repetitive scanning, where consistent coverage, speed, and positional traceability are essential.
Okay, thank you.
Small parts where repeatability is important.
Excellent. Yes. Okay. Thank you, Dr. Abhishek. So the next question is one major limitation of robotic NDT today.
Cost.
Okay. Yeah.
Integration.
Integration. Yes. Good.
Missing enabling technologies, or being unaware about the enabling technologies that are required to implement it.
Okay. Thank you. Okay, and then the last question here is, in one word, the future of NDT with robotics. Oh, that's a difficult one. Okay, so if you can, in one word.
Bright.
That's good. Thank you.
Augmented.
Yes. Okay. Very good.
Fun-filled with lots of challenges. It's not one word, but I think
It's not one word.
I think
This is
it
cheating.
summarizes it. Yeah.
Very good. Thank you, Dr. Abhishek.
Yeah,
Okay,
you can have the financial answer also, increasing margins.
Increasing margins, yes.
Which is the
about
opposite
ROI.
of cost somehow, but
Very good. Okay, so that's the end of the questions. I don't know if we've got any audience questions that have come in. I haven't seen anything pop up on my list, but I don't know, Sakshi, are you there? Have we received any questions in from listeners to the live stream? No, I think we've got anything here. Okay, so are we okay to? I'm going to hand over back to the host, I think, to Ravindra or Sakshi here. Are you okay to take this back?
Okay, so
Yeah, here we go.
yeah.
Thank you, Sakshi.
So thank you, Marcus, and a sincere thank you to all our panelists for such a deep and thought-provoking discussion. Today's session highlighted that while robotics and autonomous systems are transforming inspection, the future of NDT will depend on how effectively we combine automation, engineering expertise, and trust in inspection results. The recording of this session will be available on OnestopNDT's platforms, so please feel free to share it with your teams. Thank you all for joining us, and we look forward to seeing you at the next edition of NDT Talks. Have a wonderful evening ahead.